Welcome to this next video in which we are discussing the visual system. Okay, so in the first video we went over the anatomy of the eye and we looked at what the retina would look like if you look at it using an ophthalmoscope. Now what I want to turn my attention to is discussing the optical apparatus of the eyes, the apparatus which is going to be involved in focusing light onto the retina. Okay, so I want to begin just by discussing a little bit about the physics of light, to give you a basic understanding of the model for light that we are going to use. Then what I want to do is talk you through the motivation for why the eye needs to have some apparatus for focusing light, some refractive apparatus. Then what we'll do is talk about accommodation, and how the lens can change its shape, and by doing so we can focus light coming from different distances away. Okay, and then finally we'll discuss a few examples of refractive errors, so disorders where your vision appears blurry because this refractive process, this focusing of the light, doesn't occur properly, so short-sightedness, long-sightedness, those sort of things. Okay, right, so let's begin with a little bit about the physics of light, so the basic model of light that we're going to be using in this video. Now, if you are a physicist, if you have a physics degree, then you will have studied quantum physics, and you will know far more advanced theories of light than what I'm about to tell you. However, for our basis, the quantum theory of light is beyond the scope of this video, and we're just going to have a simple model for what light is that is good enough for us. Okay, so this is going to be my simple model of light. Okay, we are going to think of light as a little particle, and that little particle has a name. It's known as a photon, so a photon of light, and it's going to be a strange little particle because it's going to behave like a wave. So it's a particle which behaves like a wave. It does not behave like a little marble or any other little ball. Okay, it doesn't behave like a macroscopic little particle. It behaves like a wave. So it behaves like a wave. And this is the way that we're going to understand light. So it's a photon with behavior like a wave and with parameters associated with it that you'd usually think of as being associated with waves. For instance, photons have a wavelength, and this governs how they behave, because I've said that they're going to behave like a wave. So for instance, they're going to refract, which is a behavior of a wave, and the way that they will refract will be dependent on the wavelength of that photon, because the wavelength describes what sort of a wavelength wave the particle is going to behave like. Okay, so light particles have a wavelength, and you will of course know that there is a huge, great spectrum of different wavelengths that photons can have, and this is the electromagnetic spectrum. However, we are only interested in visible electromagnetic radiation, visible light, and visible photons are going to have a wavelength in between 400 to 700 nanometers. So visible photons will have a wavelength between 400 and 700 nanometers. And at the 400 nanometer side, you're going to have blue-violet. It will be a more violet-y blue than that, but this is the closest colour I have, so I'll colour it in blue there. Okay, so blue-violet colour photons would have a wavelength close to 400 nanometers, and red photons would have a wavelength up at 700 nanometers, and in between that you'd have the other colours, so sort of around 500 to 600 you'd have green in the middle, and the visible spectrum would be sort of scattered along there, so you'd have blue-green in between blue and green, and then as you go from green to red you'd go through yellow, and then orange, and then to red, etc. Okay, so the different colours of photons correspond to these different wavelength photons, and they'll behave in a different way because they'll behave like a wave with the corresponding wavelength. Okay, the other important property of light that I want to talk about. So one is colour, and that corresponds to the wavelength. The other thing that I want to talk about is intensity, so the brightness of light. So if you're looking at a really bright light compared to a really dim light, what's the correlate in this model to that? We've discussed what the correlate to colour is. It's this parameter of wavelength. Now what I want to discuss is what's the correlate of intensity, of brightness. Well, as far as our simple model is concerned, brightness is all about how many photons are actually arriving. So, you know, if you've got a shower of photons, a huge number of photons arriving, that's going to be a really bright light, whereas if you've got hardly any photons arriving, that's going to be a really dim light. So, in our model, intensity is how many photons. Okay, right, so those are the two properties of light that I want to go over with this model. Wavelength, which is this parameter of the particles, and it determines how the particles behave with these wave-like properties, and intensity, which is all about how many particles are arriving, okay, at the rate at which particles are arriving. Right, so there's the basic model of light. That's all we need to understand in order to go any further. Now what I want to talk about is, why does the eye need a focusing system? Why do we need to be able to focus light? And the refractive system within the eye, so refractive just means this changing in the direction of light, this focusing behaviour. This refractive apparatus is going to consist of the cornea and also the lens. So what I want to do is motivate why we actually need a system to focus light. And the way I'm going to do this is by imagining that we are looking at a candle. So I'm going to draw a little candle here. So here's my candle, and let's say the candle is burning. So here is the flame, and we are going to be looking at this flame. So this is a point source of light, or a very small point that is giving out light. So now let's imagine that I designed an eye which didn't have a focusing system within it, okay? So no cornea and no lens. So my eye is therefore going to look like this. Okay, here's the pupil in the middle there. We'll still have the iris going around like that. Okay, here's the retina on the back here. And now what's going to happen? Well, light from this point source is going to be diverging out all over the place, and that's the important thing. So light isn't just coming in a straight path from here to here. Instead, it's going off in all sorts of directions from here. And that means that actually light coming at multiple different angles is going to be coming through the pupil. So let me show you this. It's going to be difficult because I've drawn the pupil very small, but I still think we'll be able to show this. So there's one photon coming at this angle and hitting the retina back there. Now let me show you another photon. So here's another photon going at a very different angle and again hitting the retina, but now down here. And you can imagine that photons would be going off at all the angles in between those two photon paths, and therefore you'd get photons hitting this entire bit of the retina here. So the image of this tiny little point in the visual field, and that's actually a key word or key phrase that we're going to use throughout this video, visual field. So that's just the field of vision, what we're looking at. So this tiny little point in the visual field is actually putting light onto a huge great portion of the retina, and this is a problem. We do not want a tiny little portion of the visual field corresponding to a massive great portion of the retina, because the problem is, if I now have another candle, let's say here, I'll put another candle here, and again it's a light. When we see where the light will come from this one, and I'll actually just draw this on, so let's see where the light from this one will come. Okay. You can see that there's a very real possibility that the light from this one, the portion of the retina that this one's going to hit, is going to overlap with this one. The way I've drawn it, it hasn't quite, but you can imagine that if I brought this any closer, then this would start overlapping with this. And that's ridiculous, okay, because we've got these two separate points on the visual field that we're not going to really be able to brilliantly distinguish between, because they're both going to be shining light onto the same portion of the retina. So this would lead to the image being extremely blurry. You're getting very bad, very poor, messy information that it would be very difficult to interpret and form a clear image of the world, because a tiny point in the visual field goes onto a large portion of the retina, because of the fact that light from a point source is going to be diverging out. That's the key to what the problem is. That from a point source, you do not just have light coming in one direction, you have it going in all different directions. You have this divergence of the light. And what we need is a focusing apparatus which will refocus all the light that's coming from a single point and focus it onto a very small part of the retina. And that's the motivation for why we need a focusing system within the eye. So what I now want to do is go over this situation again. Again, we'll draw out a candle, and this time I want to draw out the eye with the focusing system in, so with the cornea and with the lens, and I want to show you what really happens now when we have the cornea and the lens, and how the light from a point source is going to be focused onto a little part of the retina, and how this is going to give rise to us having a clear image on the back of the retina. So let me draw this here. So here's another candle, and again it will be a light here, so here's the flame, and I'll draw the eye again, so we'll have the eye here, like so. There's the pupil, and this time we've got the cornea there, and we'll also have the lens, like so. So this is supposed to represent the ciliary body. It's just a basic picture, but the two key portions of the focusing apparatus are the cornea and the lens. Everyone always forgets the cornea. Everyone can remember that the lens is obviously there to focus light, but people forget the cornea, and in fact the cornea does most of the bending of the light. The lens just sort of fine-tunes it. People remember the lens because it can change its shape to change the refractive or focusing power of the overall eye apparatus here. However, the cornea actually does most of the focusing. So let me show you what's going to happen now. So firstly I'll draw a light ray that's coming directly in, so that's hitting the cornea nice and squarely, so this isn't going to be bent. So that's going to come straight in like that. Now let's imagine having one that's coming off at an angle like this. What will now happen is when it hits the cornea, it's going to refract, it's going to change direction. So this is a property of light, a property of waves in fact, called refraction. And the way in which light will refract will depend slightly on its wavelength. However, for simplicity, we won't be going into the fact that different wavelengths will refract to slightly different extents. The visual spectrum is quite a narrow spectrum of the electromagnetic spectrum. So the changes in the wavelength, the different colours of light, is not huge. And therefore, for a basic approximation, we can imagine that all of them refract equally. Okay, so what I'm saying is that we're just looking at a tiny little variation in wavelength over this visual portion of the electromagnetic radiation spectrum, and therefore we can approximately say that they all refract to the same amount. It's not quite true, and if we were being more precise, we'd acknowledge that, but for a basic understanding, we can assume that they're all refracting to an equal amount. Okay, right, so what will happen now is it all will bend, and then when it goes through the lens it will bend as well, and this is the idea that it's then going to go to the same part. And then equivalently, with one coming up here, again it will bend, and then it will bend as it goes through the lens. I've drawn it bending a little bit extreme because of course I've messed the picture up a little bit. It wouldn't have gone through the iris otherwise. But you get the overall picture here, that this divergent light is going to be refracted, it's going to change its direction, and the idea is that we reconverge it up. So here we have the convergence again, and now all of the light from this small portion of the visual field is going to be focused onto a small part of the retina, and different points at different little point sources of light at different parts of the visual field will end up being focused onto separate portions of the retina. That is the absolutely key idea here. Now, just to go over this, because I think it's very important to make sure that everyone's clear about this, which portions of the visual field are going to end up being focused onto which portions of the retina. So let's imagine that we are looking at this visual field here. So let's imagine that we've got someone standing here and we're looking at them from behind, so they're looking forwards at this visual field. Okay, we will call this the left hemifield up here. So hemi means half, so this is the left half of the visual field, because it's on the patient's left, it's on the person's left here. We call this the upper left hemifield, this the lower left hemifield, and then we'd have the right hemifield over here. So I want to show you for one of the eyes where all of these different portions of the visual field would actually be focused onto. So let's take the right hand eye. So we're going to imagine we're looking at the right hand eye from behind now. Okay, so we're imagining that we have gone through the back of someone's head and we're looking at the back of their eye. So I will divide the back of the retina here. So this is a part of the retina, 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 into 4 quadrants similarly. Now let's go over where different parts of the visual field are going to be focused to on the retina. So if I've got a point up in this quadrant here at the visual field, where is light that's coming from there actually going to be focused on? Well, think of how it's coming into the eye. It's coming down in a direction like this, so it's actually going to be focused onto this quadrant down here, and the more extreme up it is up here, the more further down here it will be. Okay? So that's the portion of the retina that visual stimuli in that portion of the visual field are going to be focused onto. Now, this quadrant up here that I'm colouring in green, and you hopefully have already got the hang of this, so the light would be coming down at an angle like this. Where's it actually going to be focused in on the retina? Well, imagine, hopefully you can visualise this, it will be coming in at this sort of angle like so, and then it will be going down, and all of that divergent light, it will be focused onto a point down here. Okay, so points in this portion of the visual field will be focused onto points in this quadrant of the retina. Next, let's have this quadrant of the visual field. So light from these points will be coming up at this sort of angle, so they're going to end up being focused onto points of the retina over here. And then finally this quadrant here, of course, light will be coming up at this sort of an angle, and it will be being focused onto points in this portion of the retina. So a point down here would end up maybe, let's think about it, would end up coming at this sort of an angle here, and therefore it would probably end up somewhere over here on the retina. All light coming from there will be focused onto there. Okay, so that's the basic idea of why we need a focusing system within our eye. It focuses points of the visual field onto points of the retina, rather than the case which you'd have if you didn't have the focusing system, where a tiny point in the visual field ended up putting light onto a huge great portion of the retina. Okay, now what we need to consider is accommodation, and I've decided that accommodation definitely does have 2 M's in it. Okay, so accommodation is what I want to discuss in more detail now. So accommodation is all about changing the shape of the lens, and what's this all about? Well, this is about focusing on objects that are different distances away from you. So I've actually made this simpler. I've ignored a complexity here. I've actually ignored loads of complexities here to make it simple, but I'm now going to highlight a complexity that I didn't dwell on when I was just discussing this, and that is that actually how difficult it is to reconverge the light that is coming from a point source is going to depend on how close that point source is to you. So let me try and demonstrate this. Let's say that we move the candle much closer to our eye. So let me try and show this. I'm going to hugely exaggerate this. So let's have our candle here. Okay, and let's now have our eye incredibly close to the candle. Okay, so here is the eye positioned here now. There's the iris and the pupil, cornea here, and the lens here. Okay, so why is it going to be much more difficult to focus the light coming from this point spot when it's much closer to the eye than if it's further away? Well, the reason is that the angle that the light rays are diverging, that are going to be entering the eye, is going to be much greater than when it's further away. So let me try and show this with this picture. I hope that this picture is going to actually communicate it. So I've drawn it as though there's going to be no, the cornea isn't going to bend it at the moment. So imagine that the cornea and the lens aren't there for the moment, and I'm just drawing this on. Can you see that these light rays are going to have a much greater angle between them, i.e. this angle between these two is going to be much greater than if the candle was much further away. So whenever we've got a candle and it's got this flame that's giving out light in all sorts of directions, not all of those light photons are actually going to get through the pupil. Only some are actually going to get through the pupil. And if the candle is much closer to us, then the angle between these different photons is going to be much greater than if the candle's much further away. I'll try and show this actually by doing a more extreme picture. So now let's have the candle there, and let's have the eye here. So there's the pupil, there's the cornea, the lens here again. But again, imagine that the refractive apparatus isn't there. All I want to show you at the moment is how the angles of the photons, of the extremal photons that are actually making it through the pupil are going to be more extreme in this case where the candle's very close to us than in this case where the candle's much further away. So I'll try and do this. So here is a photon coming, and there it goes. You can see I'm trying to get this one. It's at the upper limit of a photon that would actually get through the pupil. If it was any further up, it wouldn't have got through the pupil. And now let me show you this other one. So this one is now a bottommost one that will come through. And can you see that the angle between them is much smaller than the angle between the extremal photons that will make it through the pupil up here? That's my point here, that the photons that will actually make it through the pupil will be much more divergent when we've got it much closer up than when we've got it much further away. That's why the light coming from this point source requires more focusing power than the light coming from this point source. So I hope I've got my message across of why we need accommodation. We need to be able to change the focusing power of this optical apparatus within the eye and adapt it to these differing distances that the visual stimulus could be away from our eye. And I think we'll have a break here, and in the next video we'll continue on with this discussion of accommodation.